too far. Don't really have any administrative things. Of course, I could remind you that we have an exam coming up next week. That's the big thing that you should be thinking about. It will cover, what we're talking about today, 16.2. It'll also cover 16.3, and that will be the kind of the final stuff. Any questions before we jump into the math for today? All right. So in your pre-class video, you learned a little bit about line integrals with scalar functions. As I alluded to back in chapter 13, right, this S thing, this parameterization for arc length, right, S of t back then, does come up, and we use this ds as part of our formula. Of course, so this would be then the derivative, which has, again, this kind of important thing from arc length in it. With this good parameterization in terms of S sort of deal, although we don't have statement number 1 here quite yet, this we'll get in chapter 15, it turns out kind of these important measures in each one of our dimensions are really the integral of 1 with respect to a good parameterization. So this appears to be something in the projector. It's a little glitchy. Error in the matrix or something. But anyway, so yeah, the integral of 1 ds is arc length. The integral of 1 dA is going to be area, and the triple integral of 1 dV will be volume. So it turns out these important measures are all the integral of 1. So the full-on line integral then that we learn in here the pre-class video, we'll have a function that we can enter our parameterization into, x of t and y of t. And then this ds, right, will kind of transform into this really rate times time sort of deal, and we'll integrate with respect to t. This is in the 2-dimensional case. In the 3-dimension case, right, you can sprinkle in some z's. Of course, either one of these can be written as f of r of t times the magnitude of r prime of t dt. And then we get into an example. And like I said, there's a bit of a silly example, right, as far as what are these line integrals actually giving you. And so in this case, you imagine that you're a whale swimming around in the ocean eating plankton. Maybe at each spot in the ocean, there's some plankton density function, right? How many plankton are at each spot in the ocean? Sort of deal. You spin around in a circle, and the question is, when you add up all the plankton that you ate over swimming in that circle, how much is it? In this case, just 4. So that's what these line integrals are giving us. We're adding up some quantity, not necessarily length, but some quantity over a curve. So that can be mass, it can be plankton, it can be all sorts of things. All right, and that's the end of the pre-class video. Any questions on this one here? All right, well, we'll start off today's class with a few more examples before jumping into line integrals with vector fields. So let's go ahead here. So it looks like we're interested in building part of a wall at least. We have a parameterization given to us. T is going from 0 to pi, apparently. We have a height that we would like the wall to be, given our x and our y values here. And then we have each brick has a certain cross-sectional area, and the question is how many bricks should we bring to build this portion of the wall? So we need to add up, right? Basically, we have area under this height curve will give us our cross-sectional area, and then we'll go ahead and use some dimensional analysis to figure out how many bricks we're going to need. So in the heart of this, we are integrating our height function, xy squared ds, over the curve that's given to us. Well, the curve, right, we would like some bounds for our integral, right? And these bounds and whatnot in our curve specified to us in t stuff. So we're always going to kind of switch into t's. So when I do this, there's really kind of 2 steps. First, I need to transform my function itself. So instead of x, right, I'm going to put in the x parameterization. So instead of x, I'm going to put 2 sine of t here. And instead of y, I'm going to put 2 cosine of t. Well, this is supposed to be y squared, so there we are. We are going to go ahead and do an integral with respect to t. So we can go ahead and put our bounds for t. Right now that we've swapped into t, it's very clear what our bounds need to be here. And then the most common mistake that I see for these types of problems is that students either leave it just like this and then start to integrate, or only a hair better, they write dt and then start to integrate. But remember, right, ds is not equivalent to dt, that there's some transformation that's going on here, and these are not in general equal to one another. So there's something missing here, right? And so that's going to be this whole magnitude of r prime of t. So that's the piece that's missing. So let's spend a little bit of time calculating that out. So I could do r prime of t first. So that's going to be what, 2 cosine of t and negative 2 sine of t. And then if I do the magnitude of that, that's going to be 4 cosine squared plus 4 sine squared, all under our square root. Again, we're squaring each component, adding those together, throwing them under the square root, just like we did in the magnitude back in 12.2, a long time ago now. This one's quite nice. It simplifies, right? Because sine squared plus cosine squared is just 1. So if you factor out a 4, this is really 4 times 1 inside of the square root. Square root of 4 is just 2. So this right here, in our case, relatively nice situation, is just equal to 2. But again, if you don't include that, your answer is going to be off, right? All right, so let's go ahead and maybe I'll bring out all my constants. So if I'm counting this as a 2 here, it looks like I have 1, 2, 3, 4 2s all being multiplied together. And so I think that should be 16. We have sine of t cosine squared of t dt. Now I can go ahead and integrate. This is going to be a small u substitution, right, where u is equal to cosine. And so when I integrate this, what I'm going to have negative 1/3 cosine cubed t. Of course, you can double check. If I take the derivative of this, I should get back to where I started. So I'm not going to factor out this 1/3 quite yet. We need to evaluate that from 0 to pi. And by the way, I know that I'm doing this u substitution a bit fast. This is kind of the minimum amount of work that I would expect to see for your written work for quizzes and for exams. So this is where, if you're not quite here yet, as far as your u substitutions, that's certainly okay. You can take more steps as needed. But as far as when it comes to quizzes and exams, right, you can go this fast and still get full credit. And so this is kind of something that's maybe worthwhile to kind of push yourself towards. Question, yes.
Negative 1/3.
Well, why is it negative 1/3? So basically what I'm thinking about this as u squared, and then so u is my cosine, and then the derivative of cosine is negative sine, right? So there's going to be it's going to be off by a negative, so that's why I had to include the negative there. And then when you integrate u squared, right, you get 1/3 u cubed. So there's kind of, a few intermediate steps that I skipped there. Again, it may not be a bad idea to push yourself if you're not quite here yet to kind of get to around this level, because you can go this fast for quizzes and exams and not get marked off. All right, and then the last bit here, oops, no longer need the eraser. Negative 16/3. When I plugged in pi in for cosine, I would get -1. And if I cube that, that's still -1. And then I need to subtract away if I plugged in 0 into cosine. Cosine of 0 is 1, cube that. And that's still 1. And so this is going to be equal to what, 32/3. Thankfully, it is a positive number. I was a bit concerned with these negatives, right? It'd be kind of alarming if they had to bring a negative amount of bricks. And then our units here, right? So this is going to be, looks like meters. So the cross-sectional area here is going to be in square meters. And so this is what I meant where we need to do a little bit of a dimensional analysis. I know that my bricks are 100 square centimeters. And so let's see, in 1 meter, there's 100 centimeters. 1 meter, there's 100 centimeters. And then finally, with 100 square centimeters, this is equivalent to 1 brick. So square meters cancel with our meters here. Square centimeters cancel with our centimeters here. There's a 100 that can cancel with one of the 100s below. And it looks like there's going to need 3,200 divided by 3 bricks, which is approximately what, 1,067, we're rounding to whole numbers here, bricks. And then being good contractors, you always add 10% or something like that, right? Because it's a real pain if you don't have enough material. I haven't seen so many homework or quizzes or exam problems that have this dimensional analysis at the end. So it's just me trying to fit a real world problem in here. So if you're worried about the dimensional analysis part of this, I wouldn't be as concerned. Any questions on this problem here? Well, let's try one more. And then we can get into the line integrals with vector fields. So suppose I have a nice spring. It seems to follow this curve here. This is a nice helix. T is ranging from 0 to 8 pi in this case. And we have this given density function. And my question is, how heavy is the spring? So it is true that mass will be equal to the integral of density. In this case, it's given by this delta thing. Since we have a spring, which is kind of more of a one-dimensional item, right? We're just doing a single integral over our curve. So basically, we're adding up the weight at each one of these places. So just as before, I can go ahead and start substituting in my function here, 10 minus x minus y, and then start transforming everything in terms of t's. So 10 minus, and instead of x, I'm going to put 3 sine of t. Oops. And then minus y, and instead of y, I'm going to put 3 cosine of t. So I'm just looking up here at my parametrization to find what x and y coordinates are. Turns out we didn't need the z one. We do have this information. We will need it at least when we calculate out ds. So when I go to calculate out ds, I guess I could put my bounds for t in at any time. So I'll do that now, 0 to 8 pi. And again, the most common mistake that I see is either folks just write this and then they start to integrate it immediately, right? Or they switch ds to dt like this and start to integrate immediately. Still the most common mistake that I see. So don't forget that ds is not equal to dt, and just not writing it or just changing that to dt isn't correct. It doesn't yield a correct answer. So let's go ahead and spend a little bit of time. First calculate out the derivative and then the magnitude of that. So we're going to have what? 3 cosine of t, negative 3 sine of t, and then 4. So when I calculate out the magnitude, this will be 9 cosine squared, 9 sine squared, and 16. Again, if you factor out the 9 from the cosine squared and the sine squared, well, that's just 1. So you're going to have 9 times 1 plus 16, that's root 25, which will be very nice to us. It's just 5. So in this case, my ds is equal to 5 dt. Question, yeah. No. So yeah, the question for those online and whatnot, and maybe just didn't hear in class, question was, will this derivative, we've had 2 in a row, very nice to us, where it just solves to a constant, right? We've had 5, and then before that 2. Will that always be the case? No, sadly not. However, in general, integrals with square roots are quite difficult, right? I brought up before in class, this is kind of the basis for a lot of trigonometric substitution. So the ones that we have in class, right, they are, well, in class, in the homework, quizzes, exam. When I say class, I mean really in our course. They're not too terribly difficult, right? You don't have to use the trigonometric substitution at least. So maybe U sub, maybe on the homework, you'll see maybe a integration by parts sort of deal, but that's about the extent of it. Good. So let's go ahead and integrate. When I integrate 10, I get 10t. When I integrate sine, I get negative cosine. When I integrate cosine, I get sine. And I need to evaluate this from 0 to 8 pi. So if I plugged in 8 pi everywhere, let's see, I'd get 80 pi plus 3 cosine of 8 pi. Well, that's going to be 1 here. So 3 times 1 will be 3. And then sine of 8 pi is going to be 0. And then when I plug in 0, I'm going to have 0. 3 cosine of 0 is going to be 3, and sine of 0 is going to be 0 here. So to some extent, these 3's here are going to cancel out very nicely for us. And my answer is going to be 400 pi. We follow the units around a little bit. We have that this density function was in grams per centimeters. This small distance, their small step along our curve is going to be in centimeters. And so when you multiply those, they'll cancel out and our unit would be in grams. Any questions on this one? All right. So then, now I'd like to move into the second main topic for 16.2, and that is a different form of line integral. This is the particular case where your scalar function with your parametrization is equal to a vector field dot, and this may look familiar, this was the unit tangent vector. So this is sometimes we'll get shorthanded, as we'll see here, as f dot t. So the unit tangent vector was denoted by this capital T. This was in 13.2 when we first came up with this, right? The tangent vector was the derivative. If we want it to be a unit vector, you divide by its magnitude. So I would say that there are kind of 5 different notations that all really mean the same thing. And so I have here, right, 5 different equal signs to show you what these all are. So the first one is this f dot t ds. This would be a line integral with our vector field. So again, this is just using the fact that this right here is our unit tangent vector, and this right here is ds. Another thing that you could do that I think is a bit nice here is that you could just cancel out, right? There's a magnitude of our derivative on top and bottom here. And so I like to write this f dot r prime of t dt with our curve. And I would say that this is my favorite one. I usually call this my working definition. And so usually if they give me any of the 5, I just convert it into this one. So this one's going to be my favorite, and I invite it to be your favorite as well. It doesn't have to be, but a lot of times in class and whatnot, when I'm doing problems, if they give me any of the different 5 ways to showcase this, I pretty much always do f dot r prime of t dt. Another thing that you can do, right, given that dr dt is another way of writing r prime, so this is the Leibniz notation versus the prime notation here. We've had in differentials before that dr is equivalent to r prime of t dt. So another shorthand that you can do is f dot dr. So instead of writing the r prime of t dt, you could write just dr. Again, but this is some shorthand. It's a little bit more mysterious. I think it's more clear the second one, what you're actually doing. Then if your vector field has named components, so p's and q's and stuff like this, then you could go ahead and write this as actually evaluating that dot product out. And this is going to be what? P dx plus q dy. That would be a fine way to write that. And if you had three components, so an x, a y, and a z, you could do a line integral p dx plus q dy plus r dz. So these are the 5 different ways that you can really write out line integrals over vector fields. But again, kind of I pretty much changed them all into the f dot r prime of t dt. All right, so I think largely when I see something like this, I say, okay, that's great. We can do the calculation if I'm told to, but why would you want to, right? Why do we care about these things? So beyond just a great way of torturing math students, it turns out that it calculates out work done by a vector field. So if we take F to be a force field, applying some force to a particle or whatnot, then the work done by the field over the curve C is given by, and really you can choose any of these 5 different ones to use, but I'll just use the first one. So work is given by this line integral over our curve of f dot t ds. So this is why we're going to care about these things, is because it gives us this nice real world calculation. A little bit of a proof about why this works out. You can recall back from 12.3 that we were told that kind of locally, if you have a constant force function, a force vector, and you dot that with displacement, that will give you the work done by that force vector in moving the box or whatever it is, particle, along the displacement vector. So if we then consider a curve, and let's say it's starting at A and ending at B, sometimes you might put a little arrow just to kind of showcase which direction you've parametrized your curve in. And you have a vector field, right? So there are vectors kind of all along everywhere in space here around this curve. And you want to know, right, what's the work being done by this vector field in either pushing particles from A to B or vice versa sort of deal. And so if you kind of go to a point on our curve, and maybe it has a, at this point, our vector field vector would look something like this, right? Well, we have then our F. We have to talk a little bit about our displacement vector though, right? So our displacement vector, well, we know that we're traveling along this curve. So we know that we're going kind of tangent to the curve at this. And so a unit tangent vector, right, is really our displacement, what's going on here. So work being done at a particular point will be f dot t. And then if you want to add up the work being done at all of the points on this curve, well, then you're going to want to do a line integral. You want to add up all of the points along the curve. And what quantity do you want to add up? Well, the work that's being done at each one of those points. All right, let me pause here and see if there are any questions. I promise we're about to do an actual example. Any questions? All right, let's do an example then. I have a picture of a vector field, and I want to first determine if the work in moving a particle along the quarter circle from 0, 1 to 1, 0 is positive or negative using the picture. So I haven't told you an equation or anything for what this vector field is. And then in our next example, we'll actually do the calculation. So if I was to draw our curve, our quarter circle from 0, 1 to 1, 0. Something like this, maybe. And why don't we look at a few points here? So here's a point on our curve, and we see what our vector field's doing. And we could also draw our unit tangent vector. And likewise, maybe over here, we can guess that our vector field would be something like this. And again, we're traveling from 0, 1 to 1, 0. So we're going in this direction from 0, 1 down to 1, 0. So our tangent vector should be pointing in that direction, not off to the left. It should be pointing off to the right. Maybe another one here. Here's what our vector field vector would look like. Here is our unit tangent vector, maybe. And one more, it looks like this one's really pretty much on it. So remember from last time, I said that if the vector field is going is helping push particles in this direction, then overall we expect that the answer ought to be positive. So I'm hoping that from our last class that you will agree with me that the answer here should be positive. The other thing that we can do, right, is that we're taking dot products. So between these tangent vectors, which I've drawn in purple, and our vector field vectors, which I've drawn in green, right? Now remember, the dot product is 0 if these things are at 90-degree angle to each other. If the angle is acute, what will the dot product be again? So if it's less than 90 degrees, it's going to be positive. And if it's obtuse, it's going to be negative. So notice if you have an acute angle here, then roughly these things are heading in about the same direction. Not the exact same, mind you, but roughly the same direction. So it's helping you move along this curve. So when I take the dot product here, because we have this acute angle, not quite 90 degrees, this is going to be a positive value. And likewise here, we're going to have a positive value. Again, acute angle that our vector field is kind of roughly helping us go along this curve. It's not pushing in the opposite direction or anything like that. It's not an obtuse angle, right? If it was like this one here, right, then that'd be more interested in going off to the left. But because that angle is acute, it's kind of roughly helping. Likewise here, another acute angle, so the dot product will be positive. And then finally, this one's closer to 90 degrees. This is going to be pretty close to 0, but it is slightly positive. And so all of these dot products are positive. And so if I go and I add up all of these positive numbers, well, when you add up many positive numbers, right, your result will be positive. So this is kind of how the equation is related to this fact that I told you, if the vector field is roughly helping push particles along the curve, then it will be positive, versus if it's hurting, right, it'll be negative. So again, our goal here was to just kind of get some intuition, and this would make a perfectly fine true-false question, right? I don't need to tell you what the vector field even is. I can just give you the picture, and I can say true or false, this is positive. All right, let's actually do the calculation though. So I want to find the work done by this force field in moving our particle along the quarter circle from 0, 1 to 1, 0. This is going to be kind of combining many things from our class up until this point. So I told you that work is F dot T ds. Of course, I said whenever you have any of the 5 different formulas here for line integrals with vector fields, I pretty much always transform them into f dot r prime of t dt. And so one thing that we could do right away, well, we need to have a parametrization, right? In order to get these things in terms of t's, we need to figure out what our parametrization is. So we need to parameterize this quarter circle. That would be maybe a good first start here. So if I'm thinking about parametrizing a circle back from like 13.1 days sort of deal, well, I see that this is a circle of radius 1, right? So I probably steal a bit from Polar. Polar is awfully nice with circles. And if I was just kind of following 13.1 strictly, you know, I'd say, well, this is a good place to start, right? 1 cosine of t, 1 sine of t, t ranges from 0 to 2 pi. There's a couple issues with this. The first being, well, this is the full circle, right? So if I go from 0 to 2 pi, I don't just get this quarter circle, but I get the entire thing. So if I want to restrict down to a quarter circle, what would you recommend that I do here? Pi halves, yeah, exactly. So first of all, let's go ahead and change this to t ranges from 0 to pi halves. That's pretty good. The only issue here is if I plug in 0 into my parametrization, well, cosine of 0 is 1 and sine of 0 is 0. So at t equals 0, I'm starting off at 1, 0. And when t equals pi over 2, if you plug that in, you'll see that you're going to end up at 0, 1. And what that means is that we're starting over here at 1, 0 and ending up here at 0, 1. We're going the wrong way. I'm going in this counterclockwise direction, which I usually like, but in my problem that's given to me, right, I need to go from 0, 1 to 1, 0. I need to be going in this clockwise direction. And so we need to figure out, okay, how can I edit my parametrization to go in this good clockwise direction? Well, there's multiple ways that you can do this. I think one of the easiest things that you can do without having to switch your bounds here and whatnot is just by swapping x's and y's. If you swap your x's and y's, so now I'm going to be using sine of t, cosine of t. Notice that these are going to be swapped. And so you're going to have 0, 1 to 1, 0, which is exactly what we wanted. It still does satisfy x squared plus y squared equals 1, right? Because now instead of cosine squared plus sine squared equals 1, you're saying sine squared plus cosine squared equals 1, right? I mean, essentially the same thing. So you'll still be on the circle here. So this is one good way that you can do this without having to change too much. The only really bad way to do this that I know is tempting is to say, instead of going from 0 to 2 pi, I'm going to go from, instead of going from 0 to pi over 2, I'm going to try to go backwards in time from pi over 2 to 0. That sometimes doesn't work. And so that's the only one I wouldn't recommend running time backwards. So that's my only one that I would say that you should stay away from. There are other ways that you could do this, right? Instead of switching your x's and your y's like this, you could have made either the cosine or the sine negative. That would get it going clockwise, but then you'd have to refigure out your t values. So this is a relatively nice way to get your parametrization going in the correct direction. All right, let's finish this one out, and then I'll ask for questions, because I understand this is a bit confusing. All right, so now that I have my parametrization, I can do a couple of things. First being, right, I know what my x's and y's are in terms of t's. So instead of my vector field, which is x squared comma negative xy, I can go ahead and put in this in terms of t's using my parametrization. So now instead of x squared, I'm going to put sine squared. And instead of negative xy, I'm going to put negative sine cosine. Another thing that I can do is I can calculate out my r prime of t. So the derivative of sine is going to be cosine, and the derivative of cosine is going to be negative sine. So again, using my parameterization, I can find r prime. Now, all of this, I'm going to be integrating with respect to t. So when I look for my bounds, what should my bounds of my integral be? They should be t bounds. Well, again, in my parameterization, we talked about how t should range from 0 to pi over 2. So in order to get just this quarter circle part that we are interested in, and not the full circle, we'd like t to range from 0 to pi over 2. This right here is the most difficult thing about the problem, right? Getting this set up. After this, it should be hopefully relatively straightforward. We can do a dot product. We've done many, many dot products throughout the semester. So this is going to be sine squared t cosine of t. And then multiplying our second coordinates together here, we have negative and negative, so plus sine squared t cosine of t dt. And then I noticed that these are actually the same thing, right? So that we could go ahead and combine these if we'd like. And this is just going to be 2 of these sine squared t's cosine of t. Just because they're like terms. Now, when we integrate, I want you to think of u as sine for this one, and then du is going to be just cosine dt. So when I integrate this, I'm going to get 2/3 u cubed, which is going to be sine cubed. Double check, right? Especially if you're going a little bit fast for your u substitutions. If I take the derivative of this, do I get back to where I started? Is this truly an antiderivative? Well, if I take the derivative, the 3 would come down, nicely cancel out with the 3 in the denominator there. Reduce my power by 1, so that'd be sine squared, and then multiply by the derivative of the inside. The derivative of sine is cosine. So yes, this seems to be working out well. Now if I plug in pi over 2, sine of pi over 2 is going to be 1. And if I plug in 0, sine of 0 is going to be 0. Cube those things, they stay the same. So my final answer here is going to be 2/3. I was hoping for a positive answer. I'm glad I got one. Questions on this problem here? Yeah, so remember this has to do everything with if the vector field is helping or hurting. So you would expect a negative answer if the vector field was hurting, right? But because, right, so this vector field is, quite literally this is example 210 and example 210 again, right? So this is the same, this is a picture of my vector field x squared comma negative xy. So yes, because we thought from the first iteration that it ought to be positive, I was looking for a positive answer when we did this actually out with the calculation. But yeah, negative answer, it's not like area or volume or something like this, right? Where you'd be very concerned if you got a negative area or negative volume, right? You can have negative work, and this is just that your vector field isn't helping push the particle in the direction that it's going at all. Good. Any other questions? Oh, sorry, yes. It really depends on if it's going clockwise or counterclockwise. So let me maybe just repeat the question for anyone online and whatnot. The question was, can we make a general rule that x needs to be sine and y needs to be cosine? And sadly, not. So you will need to kind of look at the problem and decide if when you're going around the circle or ellipse or something like this, any closed curve, are you transversing it counterclockwise or clockwise? If you're going clockwise, switching it is a good way to fix that and get it to go clockwise. If you'd like it to go counterclockwise, the traditional polar method, right, where x is cosine and y is sine, works well for that. Good. Yes, one more question. Mhm. So yeah, if in the question was essentially, well, at least how I'll interpret it first, and you can tell me if I'm wrong. But if you'd use this, right? For instance, if you didn't swap and you had cosine for x and sine for y, and you use this all the way through, would you get the same answer but just off by a negative? And the answer to that is yes. So it is true that we could write out f dot t ds over some curve with a given parameterization. If you allow for the shorthand of negative c, which is where I go along the same curve but in the opposite direction. So in this case, right, I went from 0, 1 to 1, 0, oops, like this. If you go same curve but in the opposite direction, so that's what I'm going to mean by negative c, that these are just off by a negative sign. Yeah. You could. Yeah, let me repeat your question for those online and everything. So the question is, if you understand all this about how to switch directions, well, I guess first of all, we really haven't saved that much time, right? I mean, maybe this first time around when I'm explaining it, I had to explain why swapping the x's and the y's works. But in the future, right, kind of if you just see, oh, it's going clockwise, just x equals sine, y equals cosine, and you haven't really lost time. The only thing, so if you do decide to evaluate out your line integral in the opposite parameterization, you would then have to probably explain to the graders, in a sentence or so, what you're doing, right? Because looking at it, it just looks confusing, right? So that your answer would be negative 2/3. You did it wrong, and then all of a sudden you write as your final answer 2/3, right? So you're probably going to get some points marked off for this without a sentence or two explanation saying, I'm parameterizing this on purpose in the wrong direction. I understand my answer will be off by a negative. I will fix that at the end. So yeah, it is a legitimate way to do it, but it's when you're trying to convince people that you know what you're talking about, it looks like a mistake. Good. All right. So let's do another one here. I would like to evaluate out this line integral. It consists of two pieces. There's actually two segments here, and these are just line segments. So I guess the first thing, like I mentioned, this would be our p dx, q dy, r dz. And again, our vector field would be this p, q, r. So even when I see something like this, again, I'm very tempted to always kind of put it in my working definition. So I would write my f dot r prime of t dt. Oops. R prime of t dt. And it may be nice, right, to specify what the f is here, right? So our vector field is y, z, x. So again, y was next to the dx, z was next to the dy, and x was next to the dz. So those right there make up my components of my vector field. This is my p, my q, my r. All right. Well, when I go to actually evaluate this out, very similar to when we were looking for like mins and maxes back in 14.7, that this actually is the full curve consists of two pieces, two line segments. So when I go to evaluate this, I'm going to calculate out the work done on my first line segment, y, z, x. And this will have its own parameterization, and so its own r prime and all that sort of stuff as well. Then I will calculate out the work done on the second piece of the curve, our second line segment. Again, our vector field is still y, z, x. But this will have a slightly different parameterization. And then if we sum those together, that should give us the total work done across the entire curve. So we're basically going along one straight line, and then we're going along another straight line. So and those two things together make up the entire curve. All right, well, let's get to it. First thing, we need to parameterize in each one of these cases. So if we go back to 12.5, we got pretty good at parameterizing line segments. We're going to need to use that here. So if I want to parameterize this line segment, let's do the first one here. R of t would be equal to, and we need our direction vector, and we need our point that maybe we start at. So I'm going to use 2, 0, 0 is where we're starting. And then our direction vector, well, if we want to head in the direction from 2, 0, 0 to 3, 4, 5, my claim is that we need to go 1, 4, 5. That is, I need to take one step from 2 to get to 3. I need to take 4 steps from 0 to get to 4, right? And again, formally, this is just subtraction. So if you want to just kind of, what algebra am I doing in order to get that, right? Your displacement is given by subtraction. But I usually like to think about this as, all right, I'm standing at 2, 0, 0. I need to get to 3, 4, 5. How many steps do I take? And if you remember from 12.5, right, in order to get our starting and our stopping points correct and not have this line go on forever, you want your t's to range from 0 to 1. Okay, well, we can do the same sort of deal for our second line segment over here. So in this case, r of t is going to be equal to, let's see, we're starting at 3, 4, 5 in this one. And then our displacement vector, well, we need to go 0, 0, -5. Again, t is going to range from 0 to 1. Let's do two more things here while we're working with our parameterization. First is I'd like to go ahead and simplify as much as possible. So do all my vector addition and scalar multiplication. Combine these into one nice looking equation. Oops, other way around. And then we'll go ahead and take the derivative. So I have a question, right, in chat here. How do you decide to use t from 0 to 1? So yeah, I'd recommend maybe going back to 12.5. We explained this in detail, I believe, in the pre-class video in 12.5. But basically, right, in order to get your starting point to be at 2, 0, 0, well, you want to plug in a t of 0. Otherwise, you don't start at the right spot. And if you want your ending point to be 3, 4, 5, you need t to be equal to 1. So that's maybe the short explanation. But if folks aren't satisfied with that, I would again recommend that you kind of go back to 12.5, just because I see that I don't have time left today. The last thing that I want to do here, maybe in class, is calculate out the derivatives and just set these up. So if you have time, this may be worthwhile. So derivatives, and then the setup here. So 0 to 1, and instead of y, I'm putting 4t. Instead of z, I'm putting 5t. Instead of x, I'm putting 2 plus t. And then dot, my r prime is 1, 4, 5 dt. And those range from 0 to 1. For my second piece, notice that I have a different parameterization. So I have different things for x, for y, and for z. So instead of for y, I'm putting 4. Instead of z, I'm putting 5 minus 5t. And instead of x, I'm putting 3. Then when I go and I calculate out my r prime of t, right, that was 0, 0, -5. This is what I'm dot producting with. So that will be our setup there. again, the most difficult part, I think, is done. Now you can certainly take the dot product and evaluate out these line integrals, and that shouldn't be so bad. So I will put the solutions, the final results for this problem, and the other ones that we didn't get to on D12 by 3 o'clock today. So if you'd like to get the full version of these notes, they'll be available by 3 o'clock along with the recording here. So, all right, thank you very much. Have a great weekend, and I'll see you guys on Monday.